So let's begin with the ring of polynomials. Okay. Ring of polynomials. Now we have the working idea previously that what a polynomial in X means with coefficients, suppose that has been taken from the real numbers. Okay. So we know that whenever we are considering a polynomial, we can write the expression like this. Right, where this a0, a1, a2, an that has been taken as real numbers. But in general, if you consider a ring R, and if you want to write this expression in terms of the coefficients a0, a1, a2, an, which will be taken from the ring R. Okay, so that is, you consider a polynomial in X with coefficients in the ring capital R, where this n is a non-negative integer. Okay, so this n is a non-negative integer, and the coefficients ai's that has been taken from the ring R. Okay. Now, if it happens that this n is a non-zero element in the ring, then we say that the above expression is a polynomial of degree n. Okay, of degree n, where this x has been treated as an indeterminate. We do not know what is it. We say that this x is actually an indeterminate. Don't treat this as a variable. This is not a variable, this is an indeterminate. It is an unknown object. Okay. There are many confusions with this x, but still we are using the traditional expression of a polynomial that has been written here. Okay. Although we can define a polynomial in terms of sequences having zeros after a finitely many steps. Okay. Okay. Now, another confusion is that suppose you consider now one such expression, which is, suppose in particular you take real numbers as coefficients, so x plus 2x square. Okay. Now this expression can be rewritten as, suppose you put one 0 in the left. Suppose you take another expression like this. Now these expressions are different formal sums. These are different formal sums, right? Because here it is the coefficients are 0, 1, 2, and here it is 0, 1, 2, 0, right? So these are different formal sums, but we want to treat them as the same polynomial because these three will represent the same polynomial, right? Which is x plus 2x square. So that is why to overcome this confusion, we need to define formally a polynomial in the following. That is, suppose you take a ring and a polynomial fx, a polynomial, suppose we denote this by f cross bracket x with coefficients from the ring R in R is an infinite formal sum, okay, infinite formal sum. That means fx will be summation of k equal to 0 to infinity ak x to the power k. That means a0 plus a1x plus a2x square an x to the power n plus so on, where this ak's has been taken from the ring R such that ak's will be 0 for all but finitely many values. That is, that I have already told you that a polynomial can be defined in terms of a sequence where the terms of the sequence are 0 except for finitely many values of n. So that has been conceived here. That is, ak's are 0 for all but finitely many values of k. Okay. Now these ak's are called coefficients. Coefficients of fx, of the polynomial fx. Okay. Now for the largest k for which ak is non-zero, or the largest k for which ak equal to is non-zero, that means after that k all the coefficients are 0. So for the largest k for which ak is non-zero, it is defined to be the degree of that polynomial fx, denoted by degree fx. It is k. Okay. And now if no such positive k exists for which ak is non-zero, then you say that fx is a 0 degree polynomial. Okay. So if no such k greater than 0 exists, then fx is called a 0 degree polynomial. That here I should write it as positive. Yeah. largest positive k for which a k equal not equal to 0. Yeah. Then fx, so if no such k greater than 0 exists, then fx will be termed as a 0 degree. Okay. So now suppose that a k equal to 0 for all k greater than n, then this fx will take the form as I have already written previously at the beginning of the definition, that is this one. So fx is a0 plus a1x an x to the power n, where this n is non-zero. That means n is the largest positive integer for which an is non-zero. So you can say that this degree of fx is n. Okay. So this is a polynomial of degree n. Now if you consider, suppose you take any element from that ring A, from the ring R. If you take an element A from the ring R, then fx equal to A, simply A, that is, in terms of formal sum, it is A plus 0x square and so on. Okay. So this is a constant polynomial. So every element of that ring is actually a constant polynomial. So you can view the elements of ring as a polynomial in R. So every element of that ring will be a constant polynomial. Okay. So now let us denote R third bracket x as the set of all polynomials over R. That means you have considered the coefficients from that ring R. Now our motivation, our aim is to define on that Rx an addition and multiplication of polynomials to make it a ring. So define addition and multiplication on Rx. So suppose you take two polynomial, one is fx, suppose a0 plus a1x, an x to the power n is of degree n, and you take another polynomial of degree m, right? Now in between this n and m, one must be greater than the other, right? So suppose here m is greater than n, greater than equal to n. Okay. Then this fx can be written as a0 plus a1x an x to the power n plus 0x to the power n plus 1, 0x to the power n plus 2, and so on. You can take this up to x to the power n. And this gx is b0 plus b1x plus bn x to the power n plus bn plus 1 x to the power n plus 1, bn plus 2 x to the power n plus 2, and up to bm equal to x to the power n. So now you can add this fx and gx component wise if you take the addition of the coefficients component wise, that is a0 plus b0, a1 plus b1x, a2 plus b2x square, n plus bn x to the power n plus 0 plus bn plus 1, that means it is bn plus 1. And the last one is 0 plus bm, that is bm. So this is the definition of addition of two polynomials. Okay. And if you want to define multiplication, then it is very easy. Just multiply the two expressions term wise. That is, suppose you take fx and another one is gx, that has been considered above, and if you want to multiply them, in the just multiply the two expressions term wise. That means, suppose this is your a0 plus a1x, n x to the power n, and another one is b0 plus b1x, bm x to the power m. Okay. Now if you want to multiply these two expression term wise, that means suppose you start from a0, that is a0 b0 plus a0 b1x plus a0 b2 x square plus a0 b3 x cube and so on dot 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 a0 bm x to the power m, and then you come back to a1x and then multiply this a1x with the every term of this expression, this one. So a1x b0, that means a1 b0x plus a1x b1x, that means a1 b1x square, and like this way. So you are going to have a polynomial with coefficients c0, c1x, c2x square, m plus n x to the power m plus n, right? Because we consider the last term as n x to the power n multiplied with bm x to the power m, that means n bm x to the power m plus n, right? So where these ck's are, it can be written as summation j equal to 0 to k aj b k minus j, right? So therefore this is your definition of multiplication of two polynomials. Okay. So therefore, yeah. Now it should be noted that you cannot interchange these two like this. That is, suppose you take bj a k minus n, right? Yeah. So that I have already, okay, no. So R is a ring, okay, actually, okay. So you cannot write this ck as a sum of this one because I have not considered commutativity here. So unless R is a commutative ring, okay, you cannot write this ck, which is aj bk minus j, where j equal to 0 to k, as summation j equal to 0 to k bj ak minus j. You cannot write this ck in terms of this expression unless R be a commutative ring. If it is commutative, then it is okay. Okay. Right. Okay. Fine. And with respect to these two binary operations, that is with respect to plus and dot, so you will have a ring of polynomials. So Rx will form a ring, with respect to polynomial addition and multiplication. Right? That has been defined above. And in addition to this, if you consider R to be a commutative ring, then so is Rx. If R be a ring with unity 1, then you can view this 1 as a polynomial also, as a constant polynomial 1. So therefore this 1 is also the unity for the ring Rx, because if you multiply any polynomial fx with 1, that will give you fx, that is fx dot 1, right? Okay, fine. So with respect to this theorem, you are going to have many examples of rings of polynomials, which is zx, qx, rx, cx, zpx, right, hx, and there are many. If you consider any ring, then you can have a ring of polynomial. Okay. Now the question is that if R be a, so it is a problem. So suppose R be an integral domain. Okay. So here we have assumed that an integral domain is a commutative ring with unity having no divisor of 0. Okay. A commutative ring with unity having no divisor of 0. So suppose R be an integral domain, then what would be your ring of polynomial? The ring of polynomial Rx is also will be an integral domain. Why? Why it is true? Because suppose you take two polynomials, one is fx and another one is gx, and you multiply them, fx and gm. Okay, then it would be ck x to the power k, right? K equal to 0 to m plus n, where degree of fx is n and degree of gx is m, right? Okay. Now you need to check that whether this polynomial fx and gx is 0 where you have considered this fx and gx to be non-zero. That means suppose fx, gx both are non-zero polynomial. Okay, non-zero polynomial. Okay, so that means that is if you consider fx to be the expression a0 a1x an x to the power n, and gx are the expression of b0 b1x bm x to the power m. So here n must be non-zero here bm must be non-zero. So now if you multiply fx and gx, then what is your cm plus n? So cm plus n is n bm, right? Now you have already assumed that the ring R is an integral domain. That means the ring R doesn't have zero divisor, and which says that if you take any two non-zero element, then their product is also non-zero. Since n is non-zero, bm is non-zero, so their product must be non-zero, and hence the polynomial fx into gx is also, so fx equal to into gx is also a non-zero polynomial. Okay. Okay, so this proves that. So hence Rx is an integral domain.